In the previous lecture, we learned about the basics of Nanite. In this lecture, we will learn how to customize the process of converting a mesh to be Nanite enabled and about the various view modes that can be used to visualize the use of Nanite in the level. Alright, so first, in the static mesh editor, in the Nanite settings category, are these properties here which can be used to control, when converting to a Nanite mesh, how closely the Nanite mesh matches with the original source mesh. First is the preserve area property. This causes any meshes that would lose surface area due to the simplification process to redistribute that lost area to the rest of the mesh. The purpose of this is to help improve the look of leaves and grass in Nanite-enabled foliage. So you should set this property to true for all of your foliage meshes and nothing else. Next is the position precision property. So when the Nanite mesh is generated, the mesh's vertex positions will be quantized. This simply means that each vertex, every point where the mesh's edges meet, will be snapped to an imaginary 3D grid. In other words, each vertex will have its location slightly moved in order to align with this grid. This technique allows the engine developers to write algorithms that efficiently compress the mesh's data, minimize file size, and improve rendering efficiency, which improves performance. So the position precision property is used to set the size of the space between points on the 3D grid. Larger values increase the distance between points, which means on average, vertices will be moved further away from their original positions in order to align with the grid, which will cause the mesh to appear less like the original. However, this will improve performance and lower file size. And then vice versa, smaller values will cause vertices to move smaller distances, which will cause the mesh to appear more like the original, but will decrease performance and increase file size. The auto setting, which is the default, will cause the engine to choose a value that it believes strikes the perfect balance between quality and optimization, based on the size of the mesh and its triangle density. But you can manually choose a higher or lower value in order to trade off for either more quality or more optimization. And then the normal precision property is the same idea, but applies to the precision of the normals of the mesh. Okay, so next is the minimum residency property. This property specifies how much of the mesh's data should reside in memory at any given time. Any data not being stored in memory will be streamed in from the hard drive. This value is set to the minimum amount by default, which saves the most amount of memory and is ideal for most cases. But if you had, for example, a mesh that was streaming in too slowly, you could set this to a higher value to try and fix that issue. The next two properties can be used to reduce the number of triangles in the Nanite mesh. So Nanite is so efficient that you generally don't have to worry about triangle counts affecting performance. However, even though Nanite's data format is highly compressed, large triangle counts can still be an issue when it comes to the amount of disk space that your game takes up. So to give you an idea, here's how a high polygon static mesh with 4 LODs compares with a copy of that mesh that has been converted to Nanite. Both meshes have the same number of triangles and vertices, but the Nanite mesh's compressed size is almost 8 times smaller than the original meshes. So that's a big improvement. However, if we compare the Nanite mesh to a low polygon mesh, the kind you might use if you weren't using Nanite, you can see that the Nanite mesh is still significantly larger. The good news is that Epic Games is working on improving the compression even further, and expects to be able to greatly reduce disk space for Nanite meshes in the near future. But in the meantime, there may be cases where you are ready to ship your game, but its disk size is too large to be practical. In these cases, you may want to reduce the triangle count of some of your meshes in order to trim the disk size of your game. And you can do that using either the keep triangle percent property or the trim relative error property. The keep triangle percent property is used to specify the percentage of the original total number of triangles that should remain after reduction. The trim relative error property is used to specify a percentage in which any triangle with a visual impact less than that percentage of the size of the mesh will be removed. So either of these properties can be used to reduce the number of triangles in a mesh, and whichever one results in the most reduction is the property that will be used to perform the reduction. Alright, so next, when a mesh has Nanite enabled, a less detailed, non-Nanite enabled copy of the mesh will be generated called a fallback mesh. The fallback mesh will be used in place of the Nanite mesh on platforms in which Nanite is not supported. There are also cases where it's still not practical to use a highly detailed mesh, such as in hardware ray tracing reflections, light maps for baked lighting, and as a complex collision volume. So in these cases, the algorithms will use the triangles of the fallback mesh to perform their calculations instead. By default, the engine will trim 1% of the detail of the original mesh to generate the fallback mesh. But you can change the reduction settings by using the fallback triangle percent and fallback relative error properties. And if you want to view the fallback mesh, you can use the Nanite fallback show flag to toggle between viewing the fallback mesh and the Nanite mesh. Alright, so the final thing I'm going to cover in this lecture are the various view modes that are available when working with Nanite. So I'm going to go back to the level editor, and then go up to the View Modes menu, and then go down to Nanite Visualization. The first of these modes is Mask. This mode will color all the Nanite meshes in the level green, and all the non-Nanite meshes red. So you can see my lamp and rock are green because I enabled Nanite on them, and the rest of the level is red. The Triangles mode is simply used to visualize each of the individual triangles on a Nanite mesh. And then the Clusters mode is used to visualize the clusters that the triangles have been grouped into in order for Nanite to perform its level of detail optimizations. Primitives mode will color each instance of a Nanite-enabled mesh in the level, with the exception that all instances of the same instance static mesh will all be the same color. So for example, all instances of the same mesh applied in foliage mode would have the same color. And then in instances mode, every instance would get its own color, even different instances of the same foliage mesh. Overdraw mode I'll come back to in a moment. Material ID mode will simply display each material in a different color. Lightmap UV will show a color-coded representation of the UV coordinates of each Nanite mesh surface. And then Evaluate WPO will display any Nanite meshes using World Position Offset in green and the rest in red. And the reason for this mode is that even though World Position Offset is now supported with Nanite, it still requires a little additional work to get working properly. So you might still want to be able to identify those particular meshes. Okay, so as we learned earlier, when the triangles of a Nanite mesh are blocked from view, they won't be rendered. But in cases where two surfaces are close to each other and/or overlapping, Nanite can have difficulty determining which surface is on top and will end up rendering them both at the same time. This is what's known as overdraw. Small amounts of overdraw are fine and should be expected, but you should try to avoid having too much overdraw or it will lead to performance degradation. So you can use the overdraw visualization mode to see how much overdraw you have occurring in your level. Darker areas mean less overdraw and brighter areas mean more overdraw. So right now my meshes are dark purple because there's no overdraw occurring. But now I'm going to drag out multiple copies of the rock mesh. And I'm going to turn grid snapping off so that I can move them very small distances from each other. And now, if I turn overdraw mode back on, you can see that these areas here are much brighter because there is a lot of overdraw occurring there. Okay, and finally, Overview mode will show you most of the Nanite visualization modes at once, with the fully rendered scene in the middle. Alright, and that will conclude part 2 of the lecture on Nanite.